Okay, everybody, thanks for joining us today. I'm David Oaf with Preferred Utilities. I'm joined today by Steve Pelt, who is a boiler flame safeguard expert. And between the two of us, we're going to be talking today about safe practices to prevent boiler explosions. So boilers are inherently a very unsafe device. We do two things in a boiler that you really shouldn't do. We make a flammable mixture of gas and air in a confined space on the one side, and on the other side, we have steam and water that's heated to the point where it wants to become steam, but the only reason it's water is that it's held under pressure inside of the boiler pressure vessel. And if that water were allowed to expand from liquid to gas, you get about a 1400 to 1 volumetric expansion ratio, and that's why a steam side explosion can be so severe in a boiler. So they're old devices. They were invented in the mid 1800s, and boiler explosions were so common that the American Society of Mechanical Engineers was founded in 1880 to try and prevent boiler explosions. So when boilers were first invented, they were run by hand. We had firemen, and it was the fireman's job to adjust the level of the fire to try and match the steam demand. And the fireman would modulate a hand valve to try and keep the correct water level inside the boiler. And back then, boilers either fired coal or they fired oil. The fireman also had to adjust the fuel-air ratio of the burner on the fly to keep from smoking and to have a clean flame. And so boilers were originally fired by hand. They also had to keep an eye on the fire, and if the fire ever went out, they would shut off the fuel and relight the burner. Because the fire goes out, you're just going to keep putting more fuel into the boiler, which is not what you want to do. So eventually, we automated running boilers. We automated the steam pressure control. We automated the drum level control, and we put limit switches on the boiler to shut down the burner in case the boiler operated in an unsafe condition. And firemen kind of evolved into boiler operators. And back in the day, boiler operators had to have special training to operate a boiler. You used to have what they called an unlimited steam engineer license. Nowadays, most states don't require licenses to run a boiler. A lot of states just require that someone be available to respond to an alarm. And so at most facilities, the person that responds to an alarm is just a facility person, or it could be a janitor. I've worked in hospitals where if a boiler trips, the person that hits the reset button might have been working on a hospital bed before the alarm went off, and now he's pushing the reset button on a boiler and has no specialized boiler training at all. So as we've gone from firemen to boiler operators to janitors now running boilers, it's become important that the automation that we put into these boilers works correctly and runs the boiler safely, because there's no human supervision of boilers really anymore. They're all run in automatic, and they're run mostly unattended. So it's important that the burner and controls engineers need to design the burners correctly. And the code that we follow for the burners and controls now is NFPA 85. The programs in these controls are either canned, or sometimes they're custom built. So the programmers have to make sure that their code has no errors. And when we build these flame safeguard panels, we need to QC them to make sure that no mistakes get past the QC people and make it out to the field. So there's 4 main causes of boiler explosions. There's a steam side explosion, where the pressure vessel just loses containment and you flash all the water in the boiler to steam. There's dry boiler firing, where you run the boiler out of water. There's a fuel side hard light off, and then there's a fuel side rich combustion. And I've been a boiler technician since about 1990, and done boiler service on and off from that time since. And I think Steve's been in this industry a little longer than I have. And whenever we hear about a boiler explosion, we try and find out what the cause of it was. And normally it's operator error, but we're always looking to see if it was something that was inherent in the design, or something that failed in the design, because um, whether it's human error or not, it's our responsibility to try and prevent these to the extent possible.
David, what's been your experience on what actually causes most of the time the fuel side rich combustion or explosion, if you will, incident?
It's the fuel side rich combustion. I've seen a couple of explosions that happen that way because a technician was sloppy. And I've seen back in the old days when things were linkage systems, a linkage would slip, or the linkage just wasn't done right. The linkage wasn't drilled and pinned, so the linkage slipped, and they had fuel-rich combustion. Back when I was working in California, there was a technician that blew the top off a water tube boiler twice while he was trying to start it up with a low NOx burner.
Ouch.
So our nickname for him was Boom Boom.
Well, I do know from my side, when it comes to firing oil, and if something isn't lighting off and the operator just keeps trying and trying, they can really cause a dangerous situation when we're talking about oil. Would you
Yeah,
concur?
oil is especially dangerous because oil is just a lot more BTU rich than gas, and you can put a lot of BTUs in a furnace very quickly, oil firing. So I've got a slide coming up where we're going to talk about the particular things you have to do for boiler safety when firing oil. And one thing I'd like to mention, I've got a lot of pictures that I found on the internet of blown up boilers. All the boiler manufacturers and burner manufacturers in the United States all follow NFPA 85, and they all do everything they can to prevent explosions. There isn't anybody in the US that's reckless or doesn't follow code. So, no matter who you buy a boiler from, it's going to be built. It's going to be built to code. So we're going to start with steam side explosions. In a steam side explosion, you basically develop too much steam pressure for the boiler pressure vessel to handle. And what prevents that is, first of all, firing rate control. The firing rate control is going to manipulate the burner from high fire to low fire and try and maintain steam pressure. And if the steam pressure gets over set point, the burner's going to run to low fire and sit there, and hopefully you have more load than you have steam generation, and you'll dissipate the steam. If that's not enough, if the plant just has no load at all, your steam pressure is going to creep up, and then your operating steam pressure switch is going to open. And this shuts down the burner, usually without an alarm. We call that a recycle interlock. So the operating steam pressure switch opens, the burner shuts off, no alarm goes off, and the boiler's just quiet, which can freak people out. But that's a normal condition for a boiler that has an operating pressure switch. If that fails to work for some reason, there's another switch that we call a high steam pressure switch or an overpressure switch, and it's in the non-recycle interlock circuit, so that when that switch opens, it trips the burner, and the alarm goes off, the horn goes off, and the burner won't relight unless somebody comes and pushes the reset button. So steam side explosions are so violent that we're required to have more safeties. So boilers are always required to have at least one pressure relief valve. And I think it's when they go from CSD to NFPA 85 that they're required to have two pressure relief valves, and they're usually set about 5 psi apart. And each pressure relief valve is required to be sized so it can relieve all the steam generating capacity of the burner. The VA hospital system, when you commission a new boiler, they require you to deliberately overpressure the boiler and test the steam safety valves, the relief valves. and they want to see that the relief valve opens at the pressure it's supposed to, and that the pressure doesn't accumulate more than a certain percentage while the burner's running at high fire, relieving through one of the safeties. And it's a very, very loud test, and only the VA hospital system requires this on new boilers. But I did this once and had the fire department called on me. They thought the boiler room had blown up, but it's just a really loud valve discharging a bunch of steam. So this is what the safety relief valves look like. They're spring-loaded pop-off valves, and those little handles you see on the left there are designed for you to help the valve lift if you want to test the safety. And then the discharge piping is shown there on the right, and it's got a discharge usually up and through the roof to a safe location. They're required to have labels on them so you can see the set points and the relief capacity. So whenever we're starting up a new boiler, our technicians are trained to make sure that the safety relief valves are sized properly and have set points that are reasonable for the design pressure of the boiler. So if we have a 200 PSI design boiler that's going to operate at 100, it'd be normal to have safeties at say 120 and 125. We just want to make sure that they're going to relieve below the design pressure of the boiler.
How often are those pressure relief valves tested?
In the VA hospital system, they're tested once a year. I don't think they're tested during an annual inspection on a non-VA hospital boiler. But if I'm wrong about that, hopefully somebody will put a comment into the chat if we have a boiler inspector listening live. So when we're designing a boiler or doing the burners and controls for it, we need to make sure we select the correct operating steam pressure and high steam pressure switches for the design pressure. And these are going to be set at lower pressures than the safety relief valves. They need to be shown correctly on the wiring schematic. In most instances, the operating pressure switch is going to be in the running interlock circuit, so that if that opens, the boiler just shuts down and waits for the steam pressure to go down. The high steam pressure switch with the manual reset is going to be in the non-recycle limit circuit, the 3DP circuit on like a Fire IU110, and that circuit opens, the burner shuts down, an alarm goes off, and you can't restart the burner without hitting the reset button. We are not allowed to have isolation valves between these switches and the boiler. That way, we can't have a closed valve kind of disabling our switch. And then a lot of times these switches can't take steam pressure, so you're going to see a pigtail between the steam line and the pressure switch. And I just noticed that this boiler doesn't have any pigtails on it, and I'm pretty sure this is a steam boiler too. So for the technician, it's important that they inspect the installation of the operating steam pressure switches and the high steam pressure switches and make sure they're piped and wired correctly and there aren't any isolation valves. And then to test these switches, you need to slowly raise the pressure on the boiler and then make sure the boiler shuts off on these switches at the pressure that you anticipate. And this is easy, and this usually happens while they're trying to set the fuel-air ratio curve. There's usually not enough load for us to get to high fire, so we're going as quickly as we can at high fire to get our last couple of points in before we trip on the operating steam pressure switch. But you know, the best way to set this is trial and error. If you're trying for 125 psi set point and it trips at 120, you know, you'll crank it down a little bit and then try it again until you get it there. You don't typically bench set these switches, you usually set them you know, with live steam. So the next most common cause of boiler explosions is dry firing. And I have seen boilers dry fired. I have not seen one explode because it was dry fired. And what happens here is, for one reason or another, the boiler runs out of water. And what happens is the boiler runs out of water, so the steam flow goes to zero, and the steam pressure starts going down because there's no steam in the system. And when that happens, the firing rate control or the steam pressure control is going to send the burner to 100% firing rate. So now you've got maximum heat input and no water in the boiler. And the water is responsible for cooling all the metal components in the boiler that are in contact with the flame. So without that water, the metal just keeps getting hotter and hotter and hotter and hotter. And the best thing that can happen in this situation is that somebody notices and shuts down the burner, and the boiler will sag. The boiler in this picture is typical of a Scotch Marine boiler. They're kind of held up by saddles, one in the front and one in the back. I've seen where the metal has gotten so hot that the boiler just sags between those two saddles, and the boiler is a total loss. And that's really the best thing that can happen in this situation. The worst thing is an operator sees that there's no water in the glass and then kicks on the feed water pump again or opens a hand valve. You know, sometimes the feed water pump will trip, and that's the reason that you run out of water. If you restore that water right away, the water hits that red hot steel, and you get that 1400 to 1 volumetric expansion and cause a big steam side explosion. When you see the boiler, you know, off its foundation and sitting upside down outside the boiler room, that's often the result of dry firing. So there's a lot of systems in a boiler to make sure this doesn't happen. And the first is the feed water control system. There's going to be some way of monitoring the level of the boiler in the water. And the simplest is on-off control, where there's just a level switch. And when the water gets to a certain level, the feed water pump comes on and continues to run until the water reaches a higher level, and then it kicks off. So that's called on-off feed water control. And it's common on small boilers. I'd say below 100 horsepower, on-off feed water control is more common than modulating. But your feed water pump has a motor starter on it, so the feed water pump can trip. Somebody can close a hand valve. You can get a massive leak. Somebody doesn't tighten up a union on the feed water line. All your feed water is going on the boiler room floor. There's lots of things that can go wrong in a feed water system. So the first thing that's designed to detect a problem with the feed water is your low water alarm. And the low water alarm just sounds an alarm when the water reaches set point to let the operators know that there's something wrong with the feed water system. The next is a low water cutout switch. And the low water cutout switch can be in the recycle limit circuit, or it can be in the non-recycle limit circuit. So sometimes the boiler will hit that low water cutout and the burner will just shut off and wait for the water level to be restored. On other boilers, it's in the non-recycle limit circuit. So your first low water cutout switch trips the burner, and you have to restore the water level. Then you have to hit the reset button for it to restart. And then secondly, you're going to have an auxiliary low water cutout switch. And in a lot of places, the auxiliary low water cutoff switch has to be a different technology than the low water cutoff switch. And the auxiliary low water cutout switch is always in the non-recycle limit circuit, you know, requiring a manual reset. And then there's one last thing that you can do to prevent running a boiler dry, and this is not required by code. It's you install a high stack temperature switch, or you use a controller like preferred two most recent controllers, our BurnerMate Universal and our FlexFit. They both have inputs for thermocouples that go into the stack. And the software allows you to set a high stack temperature software switch, so that if the thermocouple sees temperature higher than the set point you put in, it trips the burner offline. We like this switch because, or we like this input because it's hard for an operator to jumper a thermocouple. You know, a thermocouple signal's a hard one to fake. There was a boiler about a year ago that belonged to the military where they they ran the boiler out of water and melted it down. This is a big water tube boiler, and fortunately they didn't put water in the boiler, so they didn't blow it up, but the boiler got hot enough to start the building on fire that the boiler was in. And what the investigation showed was that one of the operators had jumpered all of the limits on the boiler. And so the boiler wouldn't trip on anything. And the operator knew he was doing something he wasn't supposed to do, so he wrote it in the logbook that he jumpered all the limits on the boiler per the direction of his boss. And our guys were baffled. The boiler had a preferred control system on it. Our guys were baffled because the day after the explosion, they went and tested the control system, and everything worked just fine. And then one of our guys went through the logbook and found this entry. But you know, older flame safeguard systems have limit strings that are relatively easy for operators to jumper. It's hard to jumper a thermocouple, so we like to include this safety feature on all of our boilers.
It is amazing though how many, standard flame safeguard are out there in operation still, and the wiring of a, recycle versus non-recycle is extremely important. And unfortunately, there's so many out there that if they're having a low water alarm, someone that doesn't understand would possibly, jumper that around and can really cause a terrible situation. So non-recycle, when referring to that, obviously means that it's going to lock out the flame safeguard until somebody resets. A recycle type alarm basically is just like removing the call for heat and then reapplying it once that alarm or switch has been satisfied again.
Boiler operators are under a lot of pressure to maintain header pressure and keep boilers running, and especially the night shift that doesn't get as much training, they're the ones that seem like they're more likely to lean on the reset button and just keep resetting a boiler without really figuring out what's going wrong, or figure out a way to disable the limits to keep nuisance trips from happening. So when we design the burners and boilers, we need to make sure we design the feed water system to exceed the boiler water consumption and safety blow-off pressure. So the feed water pumps are supposed to be sized to exceed the venting capacity of the safety relief valves. And we need to make sure we call out the appropriate low water alarms, low water cutouts, and auxiliary low water cutouts for that type of boiler and for that customer. And then correctly design and call out a high stack temperature alarm and shutdown. We beat this to death, but the high stack temperature shutdown is a hard limit to jumper. So there's been more than one instance in the past few years where, for one reason or another, the low water cutouts on a boiler didn't work, but the high stack temperature switch did, or high stack temperature input is what shut down the boiler and saved the boiler. So for the technician, it's up to the technicians to make sure that these systems are working. If you have a high stack temperature shutdown or alarm, test it, make sure it's working. Make sure it's wired into the flame safeguard correctly. Make sure that you're getting normal stack temperatures out of the boiler. And one note, it's the boiler technician on a new boiler startup that's ultimately responsible for making sure that all the limits on the boiler work. So they have to fix everybody's mistakes. If there's a mistake in the field wiring, it's their job to find it and fix it. The same with factory wiring, and the same, potentially with factory programming. And boiler technicians, they have the level of training of old-timey firemen. They can run a boiler and completely in hand, and they do to an extent before they get the automatic controls working. But it's their responsibility to test and make sure that all the safeties on a boiler are working. And the preferred technicians, when everything's done and they're assured that it's working, they get somebody from the plant and they repeat all these tests again, so that the plant can witness that the boiler shuts down on high steam pressure and low water, and low gas pressure, and everything is supposed to shut down on, and the customer can sign off that it was tested in their presence. So the third leading cause of a boiler explosion is a hard light off. This is when instead of lighting off with the smallest flame possible and getting a nice gentle light off, you light off with a bunch of fuel in the furnace. And there's several different ways that this fuel can get into the furnace, and we're going to talk about each of them and how they're prevented. But the design of the fuel trains per NFPA is done to prevent a hard light off. So your gas and your oil lines are supposed to have 2 safety shutoff valves, and the gas line will have a vent valve between them. And that's to make sure that you don't get any gas into the furnace when the burner is shut down. The next thing we do is when we go through a light off cycle, we go through purge, and we're going to purge 4 to 8 air volumes of air through the burner, just in case there was any combustibles in the burner due to a leaky gas train or any other cause. We're going to purge out all that volume and make sure there's anything combustible in there. The gas trains are required to have low gas pressure and high gas pressure switches, and they need to be sized correctly for the gas supply. And then the fuel flow control valve has to be sized for the fuel input, the supply pressure, and the turn down that's expected in the boiler. So it's the technician's responsibility to make sure the fuel system is piped correctly. The technician needs to verify that the fuel supply matches the drawings and the bills of materials and the burner nameplate. And then what's really important too is that the technician needs to know the opening direction of the fuel, the air, and the atomizing servos. This is really important, and this has caused one explosion that I know of that resulted in a serious injury. It was about 15 years ago, but a technician was trying to light off a burner on oil, and he thought that his oil flow control valve was at low fire, and it was really at high fire. So he went through a couple of light off attempts and put a lot of oil into a hot furnace, and that oil vaporized and eventually ignited and blew the front door off the boiler, and hit the technician and kind of pancaked him to the roll-up door. So it's terrible, but a lot of times the flow control valves we use in these trains are not well marked. If you use a V-ball or a butterfly valve, a lot of times the only indication of where the wafer is on the top of the valve stem, and then we usually put a servo coupling and a servo on top of that. So the only indication you have of whether the valve's open or closed is hidden under a servo coupling. So our technicians are trained that if the valve isn't marked and they're not 100% certain the valve is open or closed at a certain position, that they're supposed to take the fuel train apart and visually look inside to see where the valve is, because this has caused more than one hard light off, and it's just unfortunate. There's a million different manufacturers of flow control valves too, and some of them don't do a good job of labeling their valves. Hauk does a good job. The Hauk oil valves always have a nice label on them. A lot of times, the shaft that comes out of the top of the valve will be a D shaft, and the flat part of the D is perpendicular. The flat part of the D is parallel to the wafer, so you can visualize that and see if the valve is full open or full closed. But there's a lot of brands that you can't tell, and you have to open them up, and it's a shame the manufacturers aren't smarter.
I've actually run into a situation where parallel positioning was being added onto a application, and unfortunately the butterfly valve for the gas was basically unmarked, and there was just no way of knowing without breaking it all apart, and that's what we had to do because we couldn't make any assumptions. There was a slight mark, but guess what? That wasn't correct. So breaking it apart was absolutely necessary to find the full closed position because it was a true 360-degree, butterfly valve.
Yeah, and you did the right thing by breaking the fuel train apart to see, but um, I guess maybe the manufacturers supply these valves for a lot of different applications, and most of them are not as critical as fuel supply to a boiler, and that's how they get away with not marking their valves. The same is true of the stack damper. So you've got to make sure the stack damper is either fixed open or is open during purge. Most boilers come with a stack damper these days, and in most instances, they're just fixed open by some way. And I've had a couple of stack dampers slide closed on me while firing. So now it's just part of my checklist to make sure that whatever mechanism is holding that stack damper open is nice and solid. And if the job doesn't have draft control on it, um, sometimes I'll get the contractor to put a stitch a little weld in that mechanism to make sure that the stack damper can't close. If the job does have draft controls where the stack damper is made to modulate, it needs to be paired with a high furnace pressure switch. That way, if the furnace pressure gets too high, then the controls will automatically shut down. And what we're looking at in this top photo here is a preferred E-Link damper with a preferred servo with the cover off and a JC22 transmitter, and that sensing line you see there is for the draft transmitter that has a built-in high furnace pressure switch inside that little enclosure. So it's very important. Any of your control valves or dampers, you need to know which way is open and which way is closed. And because I'm old, I carry a Sharpie around with me now, and I just mark on everybody's equipment. So I'll draw an arrow on it to open, arrow to close. I've never gotten in trouble for sharpieing on somebody's equipment.
I've actually commissioned a parallel positioning system where from the burner manufacturer, they actually had set the servo to where the full closed position was, guess what? Past the
100%.
zero. It was past the zero or full closed on the other side of it. So you actually at 10% open, supposedly, that was the full closed, and then it started opening. And this really was weird trying to light this off properly. And so again, it was one of those things that someone didn't do something right. The full closed was not the full closed. It was like a minus 10 degrees. So it can be problematic.
I've had that happen, and it's a hard thing to diagnose
Yes,
because
sir.
you'll be too rich, and you'll try and you try and close down on the fuel valve a little bit, and instead of less fuel, you get more fuel.
Yes.
If you have manometers on your gas line, like you should, that sort of thing's pretty easy to detect. If you
Cool.
see the manometer go in the wrong direction, that's pretty easy to detect. If you're not using a manometer at low fire, the gauges, if you have a pressure gauge, usually at low fire, the manifold pressure is so low the gauge isn't showing anything. So the only idea you have of how much heat input you're getting into the burner is by looking at the flame. And sometimes the flame can fool you.
Exactly.
Yeah, you
Well,
can be putting more gas into a flame, but if your excess air is higher, it may look like a smaller flame, even though it's got more gas. So
and I think this highlights a situation if you're doing a parallel positioning commissioning for the first time, uh, actually starting off with some air and even the gas at 0 degrees to see how it acts. And that's how I actually caught it on the second try was I just dialed the gas down all the way. And guess what? It lit off and it should not have lit off. That
wow.
was right then where the butterfly was, and we were able to correct it, loosen up the coupling, dial it in correctly, but it was interesting.
Now, if you buy a fuel valve, a fuel flow control valve, and servo from Preferred, they're going to be stroked at our factory, and I've never had an issue with that. I've never had one stroked backwards, and I've never had one sort of over traveled, what Steve just described. I think our guys are pretty careful, but our technicians are also trained to inspect it, and if it's not labeled, take it apart and check it. So the first time you light off a boiler can take a long time. And one of the things you do to make sure you get a safe light off is you close the hand valve and the main gas line the first time you light off. So you're going to go through a light off sequence. You're going to go through purge, you're going to go to low fire, and then the flame safeguard is going to energize the ignition transformer and the pilot valves. And if the flame safeguard sees flame from the scanner or from a flame rod, then it's going to open the main gas valves and you're going to light off main flame. If you close a hand valve in the main gas train, it's going to open the main gas valves, but it's not going to get any main gas. So then when pilot trial for ignition is done, usually 10 to 15 seconds in, there's not going to be any flame there, and you should shut down and the horn should go off and you should get a flame fail. So we always do that the first time around, and it just helps us make sure that the flame scanner is working and that the flame scanner is wired into the flame safeguard correctly, that you will shut down on loss of flame. Also, until your main flame is lit off, you really don't know if your gas valve and your air damper are in the right position for low fire. So the pilot gives you an indication of whether you've got the correct amount of air for light off. So an all blue or a blue and straw colored pilot flame is normal and indicates you have about the right amount of air. If you get a very, very short pilot flame that's all blue, you probably have too much air. And if you get a pilot flame that's all yellow or all orange, then you have not enough air. So it's good to run the pilot once just to give you an idea of what your airflow is. Okay, so Steve touched on this a couple of minutes ago. So the first time we light off on gas or on our first fuel, we deliberately set the gas valve position too low because we don't really know where it's supposed to be if the burner hasn't been fire tested. And if we're gonna air, we wanna air on the side of not enough gas. So we deliberately set it too low. So we let the burner light off, and I like to watch the flame from the back of the boiler as we go through light off, make sure the pilot lights off, make sure it looks okay. And if there's no flame the first time you light off, I'll just hit the reset button and try it again, because there's a gas manifold downstream of the safety shutoff valves that needs to be filled with gas. And sometimes you just don't get lit off the first time because you don't have any gas in that manifold. So I'll try a second time. If there's still no main flame the second time, I'll bump up my gas flow control valve 1 or 2 degrees and then repeat this again. And this may take 5 times of no flame. And then eventually you'll get to a point where you'll see a little bit of gas come out of the main flame. It'll get lit by the pilot, and it may not propagate all the way around the manifold, but now you know you're very close. And the next time you do it, you bump it up, and you're going to have just the gas flow you want. And on a new boiler, you may have refractory to cure, and you may have to do boil out on a new boiler. So you want a pretty small flame for curing refractory anyway. So it's not uncommon to light off with a tiny little gas flame, and if you plug your analyzer in, you're 12 to 15% stack O2, and that's kind of where you want to be for curing refractory. Most of the refractory curing instructions say to cure refractory with the smallest flame possible in the boiler. The alternative to this is your gas position is too high when you light off, and then you can light off with a whoosh. And I've never had this happen to me where I lit off with a whoosh large enough to damage anything, but it's still not something you want to do. And the closer I get to retirement, the less I want to kill myself in a boiler explosion. So I seem to be getting more and more careful as I get older. So there's a lot of things that need to be done right from the burner design perspective. We've got to design the fuel and atomizing trains per the NFPA 85 guidelines. And NFPA 85 has an annex in the back that has diagrams of what these trains should look like. Oil gets a little more complicated because, like we mentioned earlier, oil, because oil is a liquid, you can put a lot more BTUs into a furnace a lot quicker with oil than you can with gas. So it's critical that your oil flow control valve is sized correctly so that you can turn it down for a small light off. You need to make sure that your low oil pressure switch, your high oil pressure switch, your low atomizing steam pressure switch, and your low atomizing delta P switches are wired correctly into the flame safeguard. And then with oil, you want to make sure you minimize the piping length between the last shutoff valve and the burner, because the first time you go to light off, you've got to fill all that pipe with oil before you get any oil to the gun.
One thing to just mention real quick on the limit string on those pressure switches, those are all wired typically on a standard flame safeguard in series, okay? So that if any of those break, it actually is in series with the power to the fuel valves. So what it does is basically kills the power to the fuel valves with any of them opening. So this is the reason that there are to be no other like relays or anything else in series with that limit string. And each one of those have to be rated for the max current of any of those, well, the fuel valves in particular. So it's just something to keep in mind and why it was done like it was done. Any of those open, it kills the power directly to the fuel valves.
So there's a couple of different ways to do oil firing. There's steam atomization, there's air atomization, then there's pressure atomization. Steam atomization is typically only used on water tube boilers anymore. Air atomization was kind of the standard for fire tube boilers, but we're seeing more and more European burners in the US market that tend to favor pressure atomization. And you can tell a burner is pressure atomized because they'll have a little oil booster pump right on the burner that takes the oil and boosts it up to about 300 psi. And they take a ton of pressure drop across the oil tip, and that's what does their atomization. When you're steam or air atomized, you've got to get not only the right fuel amount and air amount into the boiler, you've also got to get the right atomizing media to the boiler, the right amount of atomizing steam or atomizing air. So when you go to light off on oil for the first time, if it's a gas oil boiler and you've already done gas, then you know where your air dampers should be at low fire on oil. And then you've only got to figure out where the oil flow control valve should be at light off. And you're going to repeat the same procedure we did on gas. We deliberately set the oil flow control valve position too low, and then we watch the boiler light off. And it's important on oil that you watch the boiler from the back on initial light off, because what we want to be careful of is sometimes the burner can be shooting oil into the furnace that's not getting lit by the pilot for whatever reason. So we want to make sure we're not accumulating oil on the bottom of the Morrison tube or the bottom of the furnace. So when we light off, I'm watching the back and I'm looking for oil. I'm looking for sparkles that are kind of the telltale that oil's coming out. If I think I've dropped some oil into the furnace that didn't get lit for whatever reason, I'll probably take an extra purge just to make sure that oil gets vaporized and is purged out of the boiler. And it's safer to light off oil the first time when the boiler's hot from firing gas. That way, if you do dribble some oil into the furnace, it vaporizes and purges. if you dribble oil into a cold furnace, it's hard to get it out again because it's not going to vaporize. You're going to have liquid oil sitting at the bottom. And you don't want BTUs sitting in the bottom of your boiler. So the first time I light off, if I don't see any oil, I'm not going to do anything. I'll just try again. Because the first time you light off, even if your oil flow control valve is about where it should be for light off, you've got to fill up the oil line downstream of the oil safety shutoff valve, and you've got to fill up the oil gun. So it's normal usually that you've got to fill all that the first time you try and light off. If I don't get any fire the second time and I don't see any oil sparkles coming out of the gun, then I'll start the process of bumping up my oil flow control valve a degree or two and going through the light off sequence again. And I keep doing this until I get a nice, lean, stable looking oil fire. And if I think I've sprayed a bunch of oil into the furnace, it didn't light for some reason, I'll take another purge. So I think I talked about most of this. You got to watch for oil spray during the light off. Sometimes the pilot flame doesn't light off the oil spray. Watch for oil accumulation. Take an extra purge if you need to. If you think you have oil on the furnace floor, you can always switch back to gas and burn it off. Burn gas for a few minutes, and that'll vaporize that oil and send it up the stack. And this is something technicians do. Once the technician figures out what the right oil flow control valve position is for light off, then that information is going to get saved in the fuel air ratio controller, and the boiler operators don't have to worry so much about this. The burner will light off at the right position after that. So another thing you need to look out for is drips and dribbles of oil that can accumulate in the furnace. Sometimes the oil tip isn't on right, or it's not tight, and the oil gun, it can be firing, and you're firing, it looks normal, but you could be dribbling oil. And the way I was taught to design the burners is that the tip of the oil gun should be over the refractory throat. So if there is a leak somewhere in the oil gun, it's going to run out the carrier tube that supports the oil gun, and it's going to dribble down, and it's going to dribble onto the hot refractory. And when it hits the hot refractory, it's going to vaporize and it's going to burn. What can happen is the dribbling oil, if it hits the wind box or the burner throat instead of the refractory throat, that oil won't vaporize and can run backwards and start to fill up your wind box and cause a wind box fire. I was called into a boiler in New York City that had a wind box fire, and what had happened is they were burning heavy oil, and they developed a clinker that nobody noticed. And this is before I worked for Preferred, but the boiler had a Preferred opacity monitor on it that had been jumpered out. So they were probably smoking like crazy with this big clinker in the burner, but they had disabled the opacity monitor, so it didn't shut down the boiler. And eventually the clinker got so big that there was nowhere for the oil to go, and the oil just accumulated in the wind box. This is a water tube, and got about 6 inches deep in the wind box, and then ignited and just burned up everything on the burner front.
Where do the clinkers actually develop primarily on the burner?
They usually will develop on the refractory throat. If you're impinging on the refractory throat, and there's not enough airflow there, a clinker is just a hard carbonaceous deposit, and it's usually caused by oil impingement on the refractory throat. And unfortunately, it's kind of an unstable equilibrium. So once you get that clinker there, it disrupts the airflow, it disrupts the oil flow, it'll cause a little recirculation there, and the clinker just gets bigger and bigger and bigger. And the clinker on this boiler was actually cone shaped, and it kind of mimicked the shape of the oil flame, because the oil jets and the oil flame were trying to punch a hole through this clinker and kind of eroded it into the shape of an oil flame, and it was amazing. But as soon as we opened up the access door and unbricked the access door, you could see the clinker, and we knew what had caused it. So um, it's just one of those things, and I don't even know if they teach it to combustion engineers anymore, but the tip of the oil gun should be over the refractory, so that if you do get a dribble, it hits the refractory and not the steel. So the last cause of a boiler explosion is fuel-rich combustion after you're already lit. So you've had a safe light off, everything's going fine. Now you're just running way too fuel-rich. So you've got everything you need for an explosion. You've got unburned fuel, you've got temperature. A lot of times the only thing you're missing is oxygen for an explosion. So back in the day of linkage controls, the most common way to get to run rich was to have a linkage slip. And I started out my career at Cohen Company, and all of our controls at that time, well, virtually all of them were linkage, and we designed very solid linkage systems, and our drive rods were always pinned to the shafts so that they couldn't slip. The smaller fire tube manufacturers didn't go to those lengths. So you'll see their drive rods, instead of having drilled holes, will have slots sometimes. And then a lot of times their drive levers don't get pinned to the shafts like they're supposed to. So something can slip, and now the burner is running fuel rich. There was a boiler at Texas A&M. I can't remember if this was, I've been at Preferred now for about 19 years. I can't remember if this was when I was at Preferred or my previous employer. But anyway, I got called out to take a look at this because they had an explosion, and it was about a 80,000 pound per hour water tube boiler. And what happened was they'd just gotten a new burner. They set up the new burner, and the plant did their own combustion control. And the combustion control wasn't integrated with the flame safeguard the way it was supposed to. What happens when you have separate controls like this is the flame safeguard is supposed to override the combustion control and send your gas and your oil flow control valve to low fire at light off. And that wasn't getting done, and it wasn't tested. So the first time after the burner manufacturer had been there doing initial startup, the first time the boiler tripped and the operators went to relight it, it wouldn't light off. They were losing steam pressure. So the firing rate had gone to 100%, and the interface between the flame safeguard and the combustion control wasn't working correctly to drive the flow control valves to low fire. So they tried to light this boiler off 2 or 3 times with high fire gas and low fire air. And what they ended up doing is filling the entire boiler full of gas and no air. And the boiler was hot because it had just tripped. So after about 3 attempts to light the boiler off, the operator gave up and secured the boiler and walked away from it. And then what happened is the boiler just drafted enough oxygen to blow up. And you know, it rounded out the square sides of this water tube boiler, but nobody was hurt. But that's just another example of how if the interface between flame safeguard and combustion control isn't done right, you know, something bad can happen. And this was on the technician too. The system was designed wrong, and the technician didn't catch it. So nowadays, a lot of boilers have oxygen trim on them, and oxygen trim is really designed to make up for differences in ambient air temperature and keep a boiler running at the correct stack oxygen or the correct fuel air ratio, regardless of ambient temperature. So it's kind of sold and it's designed to be an efficiency improvement, but it's also a safety. You know, if the preferred controls allow you to have a different O2 set point at every combustion point. You know, you get 10 points usually from low fire to high fire, and you can set a low oxygen alarm, and you can set a low oxygen trip, and this will this will trip the burner if the O2 ever gets too low. And you know, parallel positioning systems don't have linkages, but we still have servo couplings. So we always know where the servo is, but if the servo coupling gets loose or isn't pinned correctly, the valve or the damper can slip on the servo coupling and cause the same problem that we had with jackshaft systems, you know, with something slipping. And parallel positioning systems have feedback on the servos, so we always know where the servo is. It doesn't necessarily mean we know where the damper is or where the gas flow control valve is if something slipped. So O2 trim is not only an efficiency improvement, it's also a safety. Our representative in Puerto Rico is a big proponent of O2 trim. He tries to sell it whenever he can, even though the ambient temperature in Puerto Rico is always a beautiful 85 to 90 degrees. He likes the safety factor, and they burn a lot of oil in Puerto Rico too. So if you're burning oil and something slips and you're going a little richer, you're going to smoke. And the low O2 shutdown will alert the operators before, well, there's an alarm and a shutdown that alert the operators and shut you down if you get into a condition where you're going to smoke. And then finally, there aren't very many jurisdictions that require opacity monitors. New York City requires them, and certain applications require them. But an opacity monitor is not a bad idea for any boiler. You know, it watches the opacity across your stack, and if opacity gets too high, meaning you're smoking, it's going to alarm, and then it can be wired into the flame safeguard to shut you down. So it's not a very expensive device, and it can be a last ditch measure to detect rich combustion before it causes a problem. So on the technician side, to prevent fuel-rich combustion, the technician always makes sure that they add air before they add fuel when they're increasing firing rate. So we always take baby steps. Add a little bit of air, add a little bit of fuel. If you're tuning from high fire down, you're going to do the opposite of that. You're going to decrease air. You're going to decrease fuel, and then you're going to decrease air. In transition, you always want to be air rich and fuel lean. Once you've stored all these points, the parallel positioning system is going to keep all of your servos and all of your outputs on curve. So this isn't really an issue, but during initial firing where we're setting those fuel ratio points, it's important the technician go air first on increasing firing rate and decrease fuel first on decreasing firing rate. And the technician is going to be watching the stack oxygen and watching the CO. You know, anytime you're burning too rich, you're going to make CO, and it's also possible if you're burning too lean, you can get the flame so cold that it produces CO. And then we always train our technicians to be watching the flame. My routine is every time I make a change to the fuel air ratio control, I go and look at the flame first, because if I give it more fuel or give it more air or whatever, that effect is instantaneous on the flame. It takes a few seconds for that change to make its way through your combustion analyzer. So, you know, if I'm fighting a CO problem at low fire, say, and I think I've fixed it, I'll look in the back first to see what the flame looks like, because it's going to take 10 to 15 seconds for that change to make its way into my analyzer and for my analyzer to react. And the other reason why we always want the technicians to watch the flame is if you're having a problem with, and it's usually CO, but if you're having a problem with CO or something, your analyzer won't always tell you what the problem is. A lot of times you've got to see the flame to see what the issue is. You know, sometimes it's impingement. Sometimes you've got a bad air distribution across the burner throat that's causing a rich spot. These are things that you're not going to be able to diagnose just by looking at your analyzer. You've got to be in the habit of looking at the flame, knowing what a normal flame looks like, and then knowing what all the bad things look like too. So with oil, you've got to know what underatomization and overatomization looks like. Not enough atomizing flow and too much atomizing flow, because it's kind of a different variable than too rich or too lean. You can be just the right O2 in the back, but still having CO because your flame is underatomized, or it can be overatomized. CO really has a Goldilocks effect. Too much of something can cause CO, and too little of something can cause CO. That's why sometimes it's more difficult than a CO problem can be more difficult to diagnose and fix than a NOx problem sometimes, because there's so many different causes. If your CO gets too high, over 1,000 parts per million, or a lot of the analyzers have an automatic cutoff where they shut a valve to the sensor to keep from saturating the sensor. And if your sensor goes into that saturation mode, you want to make sure you decrease fuel, you don't increase air. Because if your analyzer is picking up a ton of CO, you're probably making a lot of unburned hydrocarbons too. So you can be in that situation where you've got an explosive mixture in the furnace, you've got plenty of hot refractory in the furnace, and the only thing you're missing is air. So the last thing you want to do in that situation is give it air. And these are, I've seen a couple of these, I've heard about technicians doing this in the past. I don't think I've had an issue doing this, but you always want to make sure you decrease fuel and don't increase air if you have a bunch of CO. And then sometimes if your CO just gets out of whack, I've seen oil flames that are smoking so bad, when you look in the back of the boiler, it looks like your oil's flame has gone out. You look at the front of the boiler, it's still lit. If that's the case, the best thing to do is just shut down. Shut down and take an extra purge. All it costs you is time to take an extra purge. It's not going to hurt anything in the boiler. So a few other things we teach our technicians. Get the feed water system working before you do the fuel air ratio control. So once the feed water system is working in automatic, that's one less thing for the technician to have to worry about when they're starting up a boiler. Because, until these automatic systems are working, a boiler technician is really like an old-timey fireman. He's running everything. So fuel air ratio, setting up the fuel air ratio control can be complicated enough. Don't add to it by having to watch the water level at the same time. So get the feed water system working. We try and tune when the plant has some load so we can get up to high fire. If you can, find an operator, explain to them what you're doing. Say, I'm at low fire now, but I'm going to be slowly walking this up over the next 30 or 40 minutes to high fire. And as I start making more steam on this boiler, I need you to back off on the other boilers. And they may have to shut down another boiler, and they're going to hate to do that. But they may need to shut down their other boilers to give you load. And what sucks about that is when you're doing that initial startup, you can't guarantee you're not going to trip the boiler. So, you convince the operator to shut off all the other boilers, and then sometimes you trip your own boiler on low water or high steam or something, and then everybody's in a panic. You're in a hurry to get lit off again to maintain steam header pressure. If there's a vent, get an operator to do the vent. Usually there'll be a steam pressure gauge right there at the header where the vent valve is located. Just tell the operator, if your normal operating pressure is 110 and we go above that, open the valve a little bit more. If we go below it, close the valve a little bit more. Get the operator to work the vent. I've had cases where it's just me and I'm trying to set the fuel air ratio control, trying to get the high fire points, which are the hardest because the plant doesn't have enough load, and I'm running back and forth trying to work the vent at the same time, and nobody needs that kind of stress. So if there's an operator that can do it, get the operator to do it, and work out some hand signals between the two of you to let them know when you're going up or down in firing rate so they can anticipate which direction you're going. And then finally, we tell our technicians, ignore your phone. You know, when you're setting up combustion on a boiler, that is way more important than anything that anybody could be calling you about. So, you know, either silence your phone or ignore it. Um, uh, there was a technician at one of the rental boiler companies last year that was killed in an explosion. He had he was like 32, 35 years of experience and was killed in an explosion. And usually, you know, Steve and I have been in this industry forever. If there's an explosion, we try and figure out why, to see if it was operator error or something that was done wrong in the controls. You know, maybe that's something that, you know, maybe there's a teaching moment there where we can do something different going forward. But this is a technician that got blown up. So, you know, when there's a technician on site, it's not going to be operator error, but it's more likely to be technician error, because the technician is kind of the fireman. I was told by somebody that worked at this company, and it wasn't official, that it wasn't this technician's fault. They were working at a refinery, and the refinery had a leak of a heavier than air combustible gas, you know, something like propane that found its way to the boiler room or to the rental boiler. But you know, that's not technician error. But normally, if there's an explosion when the technician's there, it's on the technician. So you know, the job is hard enough. Get an operator to run the other boilers, run the vent line, and ignore your phone. So we talked about this a little bit. The technician's got to drill and pin all the servo couplings. You know, parallel positioning systems are inherently safer than what we had before, because we always know where the servos are. But unless the servo is pinned to whatever it is that's driving, you don't always know, you know, whether that damper is really where it's supposed to be. And you can drill and pin, or sometimes you can get a contractor to put a little tack weld on there to hold it in place. So when we're all done, or we've got the boiler far enough along that we've tested all the limit switches, we grab the plant person in charge and trip the boiler on all the limits again, and just demonstrate all these safeties. We've got a form, we ask them to sign off so that they've witnessed that the boiler safeties operate correctly. Because you know, that's our primary defense. If there's a problem with a boiler, you know, we're going to pull out this document that says everything worked the last time our technician was here, you witnessed it working. And that was the case with the boiler that melted down, the military boiler. It had our controls on it, and our technician had done the last startup on it. And he's in sales now, but he's actually one of our best technicians, and he had all of his paperwork. He says, yes, all the low wire cutouts worked. We tested them the last time I tuned up this boiler. And then finally, you know, when everything's working and you've tuned all the PID loops and everything, it's good to just stick around and just watch the boiler run through all the different load conditions. You know, we can't be in a big hurry to get off the job site, because, you know, the longer we can spend with the boiler, watching it run, making sure everything's going correctly, the more opportunity we have to see that it's going to have an issue under certain conditions, you know, low load, high load conditions. So we want to be there and watch the boiler run for a while and make sure there aren't going to be any issues as soon as we leave. All right, Steve, do you have anything to add to that about especially the boiler tune-up and operation?
Actually, I think you really, really covered it well. The only thing I would say is one of the things that happens sometimes from the flame safeguard standpoint is you will see people using non-self-check flame scanners, UV, on applications where that boiler is just, or that burner is not cycling off on a regular basis. And this is where the self-checking scanners are absolutely necessary. Just inherently in a UV tube type flame scanner, it can actually become saturated, which means that that tube is saying or indicating to the flame safeguard that there's flame there when there may not be flame there. And that is a very dangerous situation. So If you've got a burner boiler that is not cycling completely off, and I say, every 8 hours, it needs to have a self-check scanner on it. Now, some of these applications will have an infrared scanner on it, which is inherently dynamically self-checking. So that actually works out quite well. But I did want to add that because that's something that does get overlooked, and it can be really a safety issue.
Yeah, I think that's an important point that a lot of people don't take seriously is UV tube scanners are most likely to fail showing flame. And we call that a runaway scanner. So if you've got a boiler that's running and everything's normal, the scanner can fail, and it'll fail showing flame. And what'll happen is the next time that boiler cycles off, the burner will be off, but the scanner will still be showing flame, and the flame safer will go into lockout and tell you it's false flame. What you really don't want is you've got a burner running, the scanner fails in a runaway position, and then you flame out for some reason. The only way that the flame safeguard knows the flame is on is through that scanner. And so the scanner's lying, saying it sees flame when it's not there. You're just going to keep dumping fuel into a hot furnace after the flame has gone out. So it's a very, very dangerous condition. And
flame scanner is extremely important in this whole thing. And the larger the burner, obviously, the more critical it is, but it's critical even on smaller ones. And so the self-checking scanner, the beauty of that is every so many seconds, there's actually a shutter that interrupts that sight path of the UV from the flame. And that flame safeguard is looking for that signal to drop to zero. And if for some reason it doesn't drop to zero after a certain number of shutter cycles, it will lock everything down and say, that we've got a failure here. We got a runaway UV tube. So extremely, extremely important. And if you don't have a self-checking scanner on an application where the burner is running, continuously over 8 hours, it needs to be changed to self-check.
Yeah, because the way we detect a runaway scanner is if the burner turns off on like an operating steam pressure switch and the flame doesn't turn off, the flame safeguard recognizes that as a runaway scanner, and it'll trip you on false flame and won't allow the burner to light off again until you reset. And even when you reset, as soon as you hit that reset button, the scanner is going to be reporting flame. It's just going to lock out again. The danger is, like Steve was saying, is if you have a boiler that just doesn't shut down. And a lot of boilers are like that. They just run continuously because there's plenty of load to keep them on. Those are the ones that need a self-check scanner because you don't get those periodic checks. Now, Preferred's newest flame safeguard system, our FlexFit, has a feature where if your burner hasn't cycled off in the last 24 hours, it'll cycle it off for you and check the scanner and then relight.
Fantastic feature. Fantastic.
Yeah.
No.
Does anybody else do that?
I'm not aware of anyone, David. I'm not aware of anyone.
Yeah, I only start up Preferred stuff, so somebody else has it. I wouldn't even know about it.
I have not. But the other thing probably to mention too is more and more valve checking is being used, so that for leak down test and so forth. So that's another good feature that's being added to a lot of our combustion control systems that are out there. So you will run into those, and absolutely that helps, as far as seeing that if we do have a too rapid a leak by the second in the double block and bleed, if we've got a leak down there, it will detect that if you have valve checking and or valve proving, and that will absolutely keep you from leaking fuel, in particular gas, past the valves when you're in a shutdown position, which could be dangerous. Now, a lot of times, a post purge can hide this or prevent an incident, but definitely it prevents you from lighting off and you've got fuel in the combustion chamber. So